Let's look at another problem with random variables and expectation, and we'll do it with the official terminology from the start. So it's an insurance problem. Here's the deal. You're paying $200 per year for hail damage insurance, mainly for your roof, but I guess for your windows and stuff too. Is it worth it? Ooh, that should be an S. Okay, so here's a problem where the probabilities are not set in stone like they are with a gambling game. But let's suppose, if you look at the historical record, in any particular year, 80% probability there's going to be no storm damage, no hailstorm bad enough to damage your house. 16% probability that there will be $500 worth of damage. 3% probability that there will be $2,000 worth of damage, and 2 out of 1,000, 0.2% or 0.002 probability there'll be $10,000 worth of damage. Now, this is a little bit artificial because I'm only got these 4 possible damage amounts. But let's say that the way the insurance policy is written, these are the only possible payouts they give you. They determine whether it was minor, moderate, or major, and then they give you these payouts. It's not totally unrealistic, although in a more realistic situation there'd be a sliding scale with all the variables in between, and we'll get to that. It's called a continuous random variable. This is simpler though. Okay, so we want to know if this $200 per year is worth it, or if we're getting taken here. All right, well, let's call this, instead of just using X again, let's use D for our random variable for damage. Okay, and what we've got is a table of the possible values, little d, for the random variable, big D, and the probability of that big D attains those 4 possible values, little d. Okay, and what we'd like to get is the expected loss if we were not paying the insurance. Okay, let's suppose these are the amounts that we'd have to pay out of pocket. If we were not paying for insurance, we'd actually have to pay these guys. So it's the expected loss if we didn't pay insurance. And then we could compare it to the $200 a year we do pay. Okay, so expected loss if we don't pay insurance. Well, we're going to take the probability that the damage is 0 times a payment of 0. Okay, that's going to go in here. I'm going to look at this as I'm going to make another row just like we did before. The contribution for each year, of course, for the no storm case is $0. I'll put that in math mode. Okay, plus the contribution for a minor storm, 16% chance of losing $500. We're going to count that as losing $80. Doesn't mean we really lose $80 a year, but it does mean that over like 100 years we would expect on average to lose $80 a year. So it's a good estimate for what we should expect to lose. So that's, in terms of the notation, the probability that the damage is 500 times 500. Plus, and then we continue, the probability that the damage is equal to 2,000 times 2,000, plus the probability that the damage is 10,000 times the 10,000. Okay. Alrighty, so that's going to be 0.80 times 0 plus 0.16 times 500. We've got those already. Plus 0.03 times 2,000. I'll put that in the table here. That's going to be $60. Math mode. Let's make it pretty. And then this one's going to be 2 out of 1,000 times 10,000, so that is $20. Okay, and that's going to be our last one. Plus 0.002 times 10,000. And then that's all going to add up to, let's see what it adds. Well, let's do it by hand. That's going to be 0 plus 80 plus 60 plus 20 equals $160. Okay. So if we didn't pay the insurance, if these are what we would expect to have to pay, we would end up paying on average $160 a year over a very long time to average out the fluctuations. $160 per year. Oops, that didn't go where I wanted it to. Per year. Okay, So that's another example of expected value. It's not expected payment to us, it's an expected amount we'd have to pay if we didn't have the insurance. So is this insurance a good idea? Okay, well, maybe not. Because what we're predicting is over a long, long time, we'd expect to pay $160 per year, and yet they're making us pay $200 per year. This is a very common situation. You might find this a little weird in comparison with the lottery problem. In the lottery problem, we discovered that the amount we paid was not worth the winnings. And here, it seems to be the same situation. If we didn't have the insurance, we'd have to pay $160 per year average, and they're making us pay a flat $200 per year. Well, if we're able and willing to take the risk, then we probably don't really need this kind of insurance. I don't want to say insurance is a bad idea, but in this case, if we're able and willing to take the risk, we might not want to use this insurance. The reason, and I'll tell you something, one of the reasons the insurance company can make money is that this $200 is bigger than the $160. They like this situation because they know they're going to have to pay on average of all their policyholders $160 per year, and they're getting $200 per year. So they're making money. That suggests that you're not the one making money. So why do people do insurance? It's basically this big if here. Okay, that's a very, very big if. Do you really want to pay $10,000 in this major storm, or do you even want to pay the $2,000? What if you only have $1,000 in your bank account? That's not a good situation to be in, and that's a really bad situation to be in. So people do not like risk in general, and there's really good reasons to avoid risk. And what the insurance company does is, for a fee, it takes out the risk. But there is a price to pay for avoiding that risk. And that's a very common calculation with insurance, is that on average, you might actually be better off without it, but when you really get a problem, then you might be completely sunk if you have to pay these big values. Okay. So what we can see, though, is it's another example of a random variable, this quantity that can have all these different outcomes. We looked at all the different values that could have, and we added them up. Let me just make this a little more sophisticated. This is the idea of a summation. It's the summation over all the possible values d that this random variable could have. And what I'm doing is I'm looking, so this symbol just means sum over all the possible values of the random variable d. It only has 4 values, so we ended up just making this sum. So it means just plug in all the possible values this number can have in the problem. Here's 0, 500, 2,000, 10,000 in for the little d, and then calculate this quantity 4 times and then sum them up. This is just an efficient notation in this case for this big sum. Ooh, that's getting kind of unwieldy. Okay, there we go. So when we look at this kind of pattern of look at a certain kind of outcome and look at its probability and multiply. Look at a certain numerical outcome for the random variable, look at its probability, multiply, and then sum. This is a very nice, tidy way to say that. And notice this is where we really have to use this weird notation of big letter equals small letter, because we need a variable for all the different possible values that the random variable can have. That's the little d. And then we need the big letter to indicate, okay, actually go ahead and do the experiment and see what the probability that the experiment gives you a certain answer.